A bag contains 6 pieces of paper numbered 1 through 6. A student randomly selects a piece of paper, replaces it, and randomly selects another piece of paper. Use a sample space to determine whether randomly selecting a 5 first and randomly selecting an odd number second are independent events. First, list the outcomes in the sample space. Then find the probability of selecting a 5 first. Notice that you select a 5 first in 6 of the 36 possible outcomes. So the probability of selecting a 5 first equals 6 divided by 36, or 1/6. Next, find the probability that your second number is odd. Notice that the second number is odd in 18 of the 36 possible outcomes. So the probability that the second number is odd equals 18 divided by 36, or 1/2. Next, find the probability of selecting a 5 first and an odd number second. Notice you select a 5 first and an odd number second in 3 of the 36 possible outcomes. So the probability of selecting a 5 first and an odd number second equals 3 divided by 36, or 1/12. Because 1/6 times 1/2 equals 1/12, the events are independent. A bag contains 6 pieces of paper numbered 1 through 6. A student randomly selects a piece of paper, does not replace it, and randomly selects another piece of paper. Use a sample space to determine whether randomly selecting an even number first and randomly selecting a 4 second are independent events. First, list the outcomes in the sample space. Then find the probability of selecting an even number first. Notice that you select an even number first in 15 of the 30 possible outcomes. So the probability of selecting an even number first equals 15 divided by 30, or 1/2. Next, find the probability of selecting a 4 second. Notice that you select a 4 second in 5 of the 30 possible outcomes. So the probability of selecting a 4 second equals 5 divided by 30, or 1/6. Next, find the probability of selecting an even number first and a 4 second. Notice that you select an even number first and a 4 second in 2 of the 30 possible outcomes. So the probability of selecting an even number first and a 4 second equals 2 divided by 30, or 1/15. Because 1/2 times 1/6 equals 1/12, which does not equal 1/15, the events are not independent. As part of a board game, you need to spin the spinner, which is divided into equal parts. Find the probability that you get an even number on your first spin and a number less than 3 on your second spin. Let event A be an even number on first spin, and let event B be less than 3 on second spin. The events are independent because the outcome of your second spin is not affected by the outcome of your first spin. Find the probability of each event and then multiply the probabilities. The probability of event A equals 4 divided by 8, or 1/2. The probability of event B equals 2 divided by 8, or 1/4. So the probability of A and B equals the probability of A times the probability of B, which equals 1/2 times 1/4, or 1/8, and 1/8 equals 125 thousandths. So the probability that you get an even number on your first spin and a number less than 3 on your second spin is 12 5/10%. As 9 women and 6 men are on a committee. 2 people are randomly chosen from the committee members to serve as a chairperson and a treasurer. Find the probability that both events A and B will occur. Event A, the chairperson is a man. Event B, the treasurer is a woman. Notice that the events are dependent because there is one less committee member to select from once the chairperson is selected. So find the probability of event A and the probability of event B given event A, then multiply the probabilities. Notice that 6 of the 15 people on the committee are men. So the probability of event A equals 6 divided by 15. Then notice that 9 of the remaining 14 people on the committee are women. So the probability of event B given event A equals 9 divided by 14. So the probability of A and B equals the probability of A times the probability of B given A, which equals 6 divided by 15 times 9 divided by 14, which equals 54 divided by 210, or 9/35. And 9/35 is approximately 257 thousandths. So the probability that the chairperson is a man and the treasurer is a woman is about 25 7/10%. A bag contains 10 red marbles and 5 blue marbles. You randomly select 3 marbles from the bag. What is the probability that all 3 marbles are blue when A, you replace each marble before selecting the next one, and B, you do not replace each marble before selecting the next one? Compare the probabilities. Let event A be first marble is blue, event B be second marble is blue, and event C be third marble is blue. Part A. Because you replace each marble before selecting the next one, the events are independent. So the probability of A and B and C equals the probability of A times the probability of B times the probability of C. Because 5 of the 15 marbles are blue, the probability of each event equals 5 divided by 15. So the probability of A and B and C equals 5 divided by 15 times 5 divided by 15 times 5 divided by 15, which equals 1/27th, or approximately 37 thousandths. Part B. Because you do not replace each marble before selecting the next one, the events are dependent. So the probability of A and B and C equals the probability of A times the probability of B given A times the probability of C given A and B. Because 5 of the 15 marbles are blue, the probability of A equals 5/15ths. Note that 4 of the remaining 14 marbles are blue, so the probability of B given A equals 4 divided by 14. Then notice that 3 of the remaining 13 marbles are blue, so the probability of C given A and B equals 3 divided by 13. So the probability of A and B and C equals 5 divided by 15 times 4 divided by 14 times 3 divided by 13, which equals 2/91, or approximately 22 thousandths. So you are 1/27th divided by 2/91, which is approximately 1 7/10 times more likely to select 3 blue marbles when you replace each marble before you select the next marble. A quality control inspector checks for defective parts. The table shows the results of the inspector's work. Part A. Find the probability that a defective part passes. The probability that a defective part passes equals the number of defective parts passed divided by the total number of defective parts. The table shows that the number of defective parts passed is 5, and the total number of defective parts is 5 plus 24. So the probability that a defective part passes equals 5 divided by the quantity 5 plus 24, which equals 5/29ths, or approximately 172 thousandths, or about 17 2/10%. Part B. Find the probability that a non-defective part passes. The probability that a non-defective part passes equals the number of non-defective parts passed divided by the total number of non-defective parts. The table shows that the number of non-defective parts passed is 208, and the total number of non-defective parts equals 208 plus 9. So the probability that a non-defective part passes equals 208 divided by the quantity 208 plus 9, which equals 208 divided by 217, or approximately 959 thousandths, or about 95 9/10%. A quality At a clothing store, 75% of the customers buy pants. Only 20% of the customers buy pants and a belt. What is the probability that a customer who buys pants also buys a belt? Let event A be buys pants and let event B be buys a belt. Because 75% of the customers buy pants, the probability of A equals 75 hundredths. Because 20% of the customers buy pants and a belt, the probability of A and B equals 20 hundredths. Next, find the probability of B given A. First, write the formula for conditional probability. The probability of B given A equals the probability of A and B divided by the probability of A. Because the probability of A and B is 20 hundredths and the probability of A is 75 hundredths, the probability of B given A equals 20 hundredths divided by 75 hundredths, which is approximately 267 thousandths. So the probability that a customer who buys pants also buys a belt is about 26 7/10%.